Hello, Assalamualaikum and good morning. Okay, so today we will start our lecture with chapter 1. I hope all of you have this notes that is provided in the Google Classroom. Okay, for the MEC351 chapter 1, it will tell a little bit the fundamental of refrigeration. Okay, by the definition of refrigeration means process of transferring heat from lower temperature region to higher temperature region. Means that if you have a hot sauce, cool sauce, by logic hot sauce means high temperature, cool sauce means low temperature. So by the definition of refrigeration is a process to transfer heat from high temperature region, temperature, to low temperature region. Just that is the definition of refrigeration. By the definition of heat, first law of thermodynamics, energy cannot be created nor be destroyed, but can transform into another form. Okay, for the second law of thermodynamics, by the summarize of the second law of thermodynamics, we know that in natural, heat will be transferred as naturally from low temperature region to high temperature region. As example, your cup of coffee. Right. Or I'm sorry. Okay, this is opposite of what I have mentioned. Low temperature region means the cool sauce. Okay, by it we transfer from high to low. As an example, a cup you leave it 2 or 3 minutes, the temperature will reduce, will goes down, and because this water, this cup coffee, the coffee maybe around 60 degrees of Celsius. One is high temperature region and the surrounding is low temperature region. So by the natural phenomena or natural process, heat transfer will goes from high temperature to low temperature. But for the refrigeration, we are going to do the opposite. Okay, this is refrigeration. Okay, let's say low temperature is your room. Okay, this is you in the room. Okay, in the room, we maybe want to get around 24 degree of Celsius, but Celsius in Malaysia commonly. Okay, so by the phenomena, natural phenomena, room, because your room is in the low temperature region, and sorry, by naturally, the heat outside of your room, which is at high temperature region, will transfer heat than the outside. So after 2 or 3 hours, or maybe around an hour, room also will become the same. So 32 degree or Celsius is quite thermal comfort. There is not thermal comfort. You maybe will be sweat. You cannot do your job. You cannot sleep at around 32 degree of Celsius. That's why refrigeration comes in. Okay, the refrigeration must do the process oppositely from the natural process. Okay, I will use the color of green. Wants to reduce or maintain 24 degree of Celsius by transferring heat than your room, which is lower temperature region. That is what we call refrigeration process. So by doing that, your room will remain 24 degree or lesser than 24 degree, as long as refrigeration process is going on, running on until. Let's see your comments in the YouTube live. Okay, if everything's okay, we continue with our slide. Okay, application of refrigeration. Yes, you may see it in air conditioning system, food preservation, water coolers, ice making industries, and etc. Okay, heat pump and refrigeration is almost the same in the principle, because both involve in see heat pump in Malaysia, because the climates in Malaysia is very hot long year, so we don't need the heat pump. But in the west, or four seasons country, four season climate country, they have winter, so heat pump is used in winter. Will be used during the winter climate, because heat pump is a transferring heat from cool environment to warm house. Okay, during winter, okay, I try draw a little. This is your house. Winter. I put like a snowdrop here, or 0 degree. Okay, I put, let's example, -4 degree of Celsius. In your temperature, let's say they put 24 degree of, so because 24 is like the most thermal part, is the hotter, of course, your room, your house. So by natural, high to low, which is from your house to the surrounding outside, because at the outside the degree will reduce from 24 to maybe around -4. because the temperature. So can you live at -4 degrees Celsius? No, surely you will die. -4 without heating, you will die. So there is heat pump is used. Okay, heat pump need to maintain your 24 degree in your house, so they must bring Q symbol for the heat energy from the -4 low temperature into your house 24 degree higher temperature. Okay, so the same process as refrigeration process, but the objective is different because heat pump is used to heat the home or your space, your house, in your room. But refrigeration wants to cool your room. However, they use the same principle by transferring heat from low temperature to high temperature. The opposite process of natural process, because by natural, heat will transfer from high temperature to low temperature. Okay. Okay, quite boring, yeah? Okay, let me see the picture around here. Same as me draw, same as I have drawn, but it is better lah. It is graphic. Okay, so during winter, we transfer heat from home to outside. During summer, because we want to cool down the house, so we transfer heat from home, from house to outside. During winter, you transfer heat from outside to your home. Okay, the red one means hot, that one means hot. Okay, quite same, but different objective. Okay, by this figure, it shows that if you want to do the opposite of natural process, you must put energy in, you must put the work in. So that's why we have work net in. Okay, the same as refrigeration and heat pump. If we don't give the system the work net required, so the process will back to the natural process, which is heat transfer from high temperature to low temperature. If you put work energy, then you reverse the direction from the cold refrigerated space. Transfer will heat from low temperature region to high temperature regions. If we cut off the work, so it will go back to the reverse direction. You put in the work, so you will get direction of the process from low temperature to high temperature. Okay, the same as heat pump. So that is why your refrigerator in your house and air conditioner in your house or air conditioner in your car, you need energy. In the house, the energy we need is in the form of electrical energy. Okay, in your car, the air conditioner in your car the energy comes from the engine. The engine energies come from fuel, which is chemical energy. Okay, so you put energy, you get the process. If you don't put the energy, so they become natural process. That's it. Simple as that. Okay, so we revise back. Function of refrigerator is to reject heat from refrigerated space. Function of heat pump is to supply heat to the warm house. Okay, they are both of them are different objective or function, but use the same principle of thermodynamics, which is transferring heat from cold to warm. From cold to warm. Okay. Okay, 8:30. So I'll give you 5 minutes break. Let's have a cup of tea. Okay, 5 minutes. We will continue back. Okay. Okay, so we have our break, so we can continue our lecture. Okay, the next slide shows the COP. This is one of the term that we will face it a lot of time in this entire semester. Okay, COP stands for coefficient of performance. COP. Okay, sebenarnya COP ni macam thermal efficiency lah. It's like of thermal efficiency as we learn in MEC 251 subject of thermodynamics. Okay, but for the refrigeration, we use the term COP. Okay, sometimes they call EER, efficient energy rating, but for this syllabus we use COP for the refrigeration. Okay, the equation of COP is just plain simple. It equals to output over work. Work is energy. Work is energy times direct distance. So we have work kind of power. Okay, so desired output over work input. Output over input. Energy over energy. Power over power. Simple as that. So for the COP of refrigeration, it equals to heat of transfer from low, L means low temperature regions, over the work input, the work that we put to the system, that we give to the system. If we have refrigerator in your house, so the work input is coming from electrical energy that you pay monthly to Tenaga Nasional Berhad, AMB. And the QL is the heat the refrigerator transferred from refrigerator into your surrounding. So if you can check out your refrigerator, you can put your hand at the back of the refrigerator. You will feel hot air around the back of refrigerator in your house, because that means heat is transferred from your in space of refrigerator to the surrounding of your refrigerator. Surrounding means that there is your kitchen area. Okay, but it is quite different to the heat pump, because the objective of heat pump is to transfer heat from high temperature region, because the COP of heat pump, QH, is coming from your house to the surrounding, which is outside of your house. So they measure the output is the heat you absorb from the house to release to the surrounding. So they use Q dot H. It is different symbol, but quite similar to the fundamental, which is we have learned earlier the same fundamental of thermodynamic process. Okay, let's skip first the COP. We go to the interesting one. Okay, maybe most of you are familiar with this figure, the cycle, the thermodynamic cycle. Of course, you have faced this one in your thermodynamics. The cycle which we have evaporator, compressor, condenser, turbine, because this is the Carnot cycle, the basic Carnot cycle. Okay, Okay, so for the refrigeration purpose, they reverse the direction. Obviously, the difference between this one and the Carnot cycle you learn in MEC251 is different at its direction. Okay, because the normal Carnot cycle is to get the work output. So in our refrigeration, we want to give work input because we want to extract QL. Okay, the normal cycle, the normal Carnot cycle, QH coming from above, okay, and go into the system and release heat at the QL. But okay, I try to draw a little bit. Okay, wait a second. Okay, Carnot normal. I put normal Carnot cycle. Okay, this figure shows the reverse Carnot cycle. Okay, the normal Carnot cycle, heats come from the high and release to the surrounding. Okay, so we will have the work output. But we want to reverse the direction, and because of the purpose of our refrigeration is not to get the work output. We want the work input to give in, but the objective one is to extract this heat. So that is why the direction is opposite, in the reverse direction compared to normal Carnot cycle. Okay, so the reverse should need the work input. So that is why we call the Carnot cycle. Reverse Carnot cycle. Okay. Okay, theoretical Carnot COP. Okay, this one lah. Don't worry. You maybe need to memorize this equation, or maybe not, because we don't calculate the Carnot cycle, because the Carnot cycle is the basic principle. But in the real world, reverse Carnot cycle is theoretical and impractical to be happen in real world. So the scientists and previous so long time ago, they had come with better concept. They modified the cycle, the principle, and they get the vapor compression refrigeration cycle. Okay, so we put the term ideal in front if there is no errors and uncertainties in the system. Okay, ideal vapor compression refrigeration cycles, quite a long name. Don't worry, because names means nothing. What you have to know is the principle inside it. Okay, similar to the process of Rankine cycle or gas turbine cycle, we have 4 process. Okay, so this one isentropic terms, surely you have heard it about in the MEC251. Constant pressure, also similar term. Throttling, familiar term, or maybe not. Okay, we will go it later. Okay, constant pressure is also quite a familiar term. Okay, from the process state 1 to state 2, this one, state 1 to state 2 direction. Okay, we have, what is this? This is work input. So normally that one is the compressor. Biasa dengar kan, peti sejuk ada compressor, aircon ada compressor. Kalau tak ada compressor, terus tak boleh pakai sistem tu. Tak boleh pakai peti sejuk, tak boleh pakai aircon dekat rumah. Okay, sebab ni adalah jantung dia. Okay, from state 1 to state 2, we have mechanical device here. We have compressor. So the compressor needs the energy. We call it work in. So from the state 1 to state 2, we have isentropic process. Okay. Okay, what is the isentropic process from the state 1 to state 2? Okay, refer back, there is the compression process. So that term is just at isentropic compression. Easy to memorize. State 1 to state 2. Okay, from the state 2, it has high energy or high temperature and also high pressure. So what they do is pass through the working fluid in the hose or tube, pass through the condenser. Okay, this is high temperature and high pressure. You put it in condenser, so the temperature will drop because of heat is transferred to the surrounding, means to your outside house. Okay, so when it releases the temperature after the condenser at state 3 also reduce. Pressure also pressure is the same, but in real life it will drop a little bit, slightly drops. Okay, so at the state 3 we have low temperature but the same pressure as state 2. So what we call the state 2 to state 3 process, we call it constant pressure heat removal or rejection. I put rejection here. So that name, constant pressure heat rejection. Quite easy to memorize. Okay, and then state 3 to state 4. If in the Carnot cycle, this one we have the turbine. But if we put the turbine in our system of refrigeration, we will have to increase the cost. So the peti sejuk at your house maybe around RM 1,000, 2,000 ringgit. But if we have turbine in your peti sejuk, you should expect to be 10,000 to 20,000 ringgit lah. And the maintenance is also very difficult because when you add more the device, so the maintenance will become difficult. Okay, so why not we replace the turbine with the expansion valve, because here we just want to reduce the pressure. If the turbine give a little bit of work output to increase our efficiency, but it's not worth it compared to the cost that we have now. So we don't need turbine. So they eliminate the turbine from the system. They replace it with the expansion valve. Expansion valve is the device to reduce the pressure without giving any work output. Okay, so remember that expansion valve instead of the turbine. So I erase the turbine here. Okay, so the process of state 3 to state 4, we call it throttling. Like you throttle your choke. Throttling. You squeeze your hose. You throttle your neck. So it will reduce the pressure. So throttling process in expansion device. Or sometimes we call throttling device. Okay, throttling device. Sometimes we call expansion device, sometimes we call throttling device. Okay, so the pressure will drop. So P4 much lower than P3 should be P4 equal to P1. Okay, so the temperature will also drop. So T4 much lower than T3. Okay, T4 so is the lowest temperature state compared to all 4 states. T4 is lower than T1, lower than T3, lower than T2, because T2 is the highest temperature. Okay, so at the state 4, when you have low temperature, means by natural heat will transfer to you. Okay, macam dekat panggung wayang, kalau keluar dengan awet-awet, power, tolong jangan pegang tangan. Sebab alasan pegang tangan sebenarnya, bila tangan awet tu sejuk, tangan power tu panas, bila kita pegang, sama-sama akan berlaku heat transfer. Dia akan pegang tu lama sebab nak mencapai thermal equilibrium. Okay, so sama juga dalam kes ni. Temperature 4 ni paling rendah suhu. So suhu dekat awak dalam peti sejuk atau dalam rumah lah kita nak sejukkan tu, haba akan pindah ke dalam sistem. Jadi working fluid dia akan terima haba. So bila dia terima haba, dia pun naiklah suhu dia. Sama juga awak nanti kalau lah pegang tangan dalam panggung wayang, naiklah suhu dia. Suhu nafsu dia, suhu dosa dia. Okay, boleh? So temperature 4 will increase the temperature by accepting or absorbing the heat. Then the recycle goes on until you switch off the compressor. Okay, so the TS diagram should be like this. Okay, instead of we have straight line, if we have turbine in our system, we have the slope line, because we don't produce or absorb any energy here. We just drop the pressure. So jadi condong macam ni. Boleh? So yang ni kena ingat dan awak kena try balik. Betul-betul balik. Check balik kita punya diagram ni and try faham betul-betul compared to the process dia. Sebab ni sangat penting. Ini sangat penting. Inilah basic kepada proses refrigeration. Aircon sekarang yang ada dekat luar kebanyakannya based on cycle ni. Apa nama cycle dia? We call it ideal vapor compression refrigeration cycle. Okay. Okay, yang tadilah ni sama juga. Okay, macam mana kita nak kira COP tadi kita dah belajar. COP is output over input. What is the output of the system? Outputnya kita nak ni, nak buang ni, nak ambil haba dekat sini. Kita nak sejukkan dia. So output dia adalah nilai QL. Berapa banyak yang kita absorb dekat bawah ni, QL. Okay, apa input kita? Input kita TMB, bill TMB, elektrik awak tu. Elektrik tu bagi dekat compressor. So, input energy required for the compressor to run, that is what the input. So, QL bagi dengan work in. Macam ni. So, ingatlah, ni apa COP ni akan ditanya dalam setiap soalan yang related to this chapter. What is the COP of the system? QL bagi dengan work in. Macam tu je. QL bagi dengan work in. Cuma macam mana dapatkan nilai QL? Okay, yang tu kita akan belajar sekejap lagi. Rehat dulu 5 minit. Okay, take your break. Okey, kita sambung balik. Dah saya dah explain sikit-sikit pasal ideal vapor compression cycle, tapi dia lagi senang kalau kita buat example. Sebab saya nak refresh balik awak punya understanding of thermodynamic process yang kita belajar dekat MEC351. Okay, let's do the example 1.1. Yang ni saya tunjuk, nanti awak buat balik dekat rumah. Semua dekat rumah lah sekarang. Buat balik lepas habis kelas. Boleh buat lepas waktu kelas, malam ke apa, ikut lah. Asalkan awak try balik. Sebab as long as you don't do the tutorial, the example, you don't understand the process. Okay. Kita tengok apa soalan dia. Dia cakap refrigerant 134A. Okay. Refrigerant 134A is very common working fluid. Ni selalu kita guna 134 dalam aircon kereta, dalam chiller. Okay. Ni kita namakan dia refrigerant. Untuk refrigeration, kita panggil working fluid dia refrigerant. Okay, dia kata operates on an ideal vapor compression refrigeration cycle. Okay, ni highlights the ideal, because if we have the ideal system, so kita tak payah consider heat loss, pressure loss. Okay, senang lah. Okay, dia kata okay, cycle between 0.14 and 0.8 MPa. This is the highest pressure, this is the lowest pressure. Okay, jadi first kali sampai tahap situ, awak lukis TS diagram. Sebab kita hanya ada dua line pressure, satu paling atas, satu paling bawah. So yang paling atas ni yang paling tinggi lah. Yang paling tinggi dalam soalan ni cakap 0.8. Yang paling rendah 0.14 megapascal. And then the question says if the mass flow rate of the refrigerant is 0.05 kilogram per second. Okay, awak highlightkan semua yang penting. This is mass flow rate. This is P. But which P? P1, P2, P3, P4. Okay, sebab itulah saya nak awak tadi lukis TS diagram. So awak put the state sini first, state 1, state 2, state 3, state 4. So paling tinggi yang kat atas ni adalah state 2, state 3. So pressure 2, pressure 3 adalah 0.8. Okay. Soalan yang dia minta, the rate of heat removal from the refrigerated space and the power input to the compressor. Apa yang dia nak? Dia nak heat removal from the refrigerated space. Refrigerated space ni yang sejuk, yang kita nak buang haba dia. Yang ni objektif dalam refrigeration cycle. So soalan tanya pun yang sama. Soalan nak. So heat removal maksudnya Q. Bila ada removal rate, kita ada dot kat atas ni. Maksudnya per time. Heat removal per time. So Q dot. Dalam unit kilowatt lah nanti, watt ataupun kilowatt, ataupun sometimes we use the unit of kilojoule per second, because kilojoule per second equivalent to kilowatt. And the power input to the compressor, yang ni yang biasa, W in. So power means dot, energy per time, so we put it W in lah, tak payah dot pun tak apa, sebab W we know work is the energy per time. Okay. And then B. I use the yellow color. Yellow. Okay. the rate of heat rejection to the environment. Yang ni, kita tengok TH diagram. Sini QL yang disedut, mesti dia nak buang haba. Haba buang kat mana? Dekat surrounding. Surrounding ni kat atas ni lah. Surrounding. So dia nak Q dot H. And finally, the COP. Of course, COP. COP tadi apa rumus dia? Okay, COP equal to Q dot L over work in. Simple kan? Simple lah, sebab if you get the value of Q dot L kat atas ni, dapat value work in, so awak bahagilah dengan QL bahagi work in, awak akan dapat COP. Simple, boleh jawab A, B, C. So example dah saya tunjuk dekat sini. Apa yang kita kena cari, sama macam yang kita belajar dalam thermodynamics. Nak dapatkan QL dekat sini, so we have to know the value of enthalpy dekat 1, kena tahu enthalpy dekat 4. Boleh? So enthalpy tu kena cari dekat mana? Kena cari dalam awak punya properties table. So kena buka balik properties table yang awak print yang ada dekat belakang buku masa thermodynamics tu, MEC351. Okay, cari nilai enthalpy bagi setiap state H1, H2, H3, H4. Dan senang, dah dapatkan QL adalah M dot mass flow rate. Dia dah bagi dalam soalan 0.05 times enthalpy 1 minus enthalpy 4. So kita dapat QL kat sini. Nak cari kat work in pula. So work in pun sama. Awak dapatkan nilai value H1. H1 kat bawah, tolak H2. So darab dengan M dot. M dot tu mass flow rate. Okay, COP. Okay, dapat nilai QL, dapat nilai work in. So QL bahagia dengan work in. So ni cara-cara dia nak dapatkan setiap state, enthalpy setiap state. Okay, yang ni sepatutnya saya dah tak tunjuk sebab kita dah belajar dekat MEC251 how to use your properties table, how to find the value of enthalpy or any other thermodynamic properties at that particular state you can get from the our properties table. Okay, but make sure you find the value at that correct table sebab we use the refrigerant 134A. Make sure you find the value in R134A in the properties table. Okay, jangan cara tengok dekat water pula, jangan tengok tempat lain pula. Kita ada R134A, so make sure you cari kat 134A because the question is about the R134A. If the system use another refrigerant, so we cannot use R134A properties table. Kita kena cari properties table untuk refrigerant lain tu, kalau dia pakai refrigerant lain. Okay, so kalau ada masalah nak kira, nak dapatkan jawapan ni, make sure let me know. Put your question or any problem in our WhatsApp group, so I will try to help you. Okay, but make sure you try by your own. If not, I cannot help you if you don't get the value. Awak kena try buat juga. Okay, so yang tu adalah ideal vapor compression. Bila actual, so kita kena consider ada irreversibilities. Because of the irreversibilities come from the fluid friction. Ada apa kita panggil pressure drop dalam pipe aircon, pipe refrigeration system tu. Mesti ada fluid friction antara pipe and the refrigerant. Pressure akan drop. Kalau makin panjang pipe tu, makin banyaklah drop dia. Okay, tu sebenarnya kita kena consider. But for the ideal system, we ignore it. We ignore them. Okay, Yang second things of the irreversibilities adalah heat transfer loss, heat loss. Okay, sebab tu kita ada nampak dekat pipe-pipe aircon, kalau awak nampak ada air menitik. Sebab air terkondens dekat luar, air udara dekat luar terkondens. Sebab apa terkondens? Sebab dia tersentuh dengan udara luar, so ada heat loss. Udara luar kacau dah. Sepatutnya dia hanya keluarkan heat dia melalui heat exchanger, melalui condenser saja. Tapi ada berlaku dekat sepanjang pipe. Sebab tu lah kita consider dia heat loss. Okay, to real life. Kalau awak nak betul-betul kira untuk real life, kita kena consider semua ni. Okay, asalnya for ideal vapor compression cycle, we have this TS diagram. Cantik, straight line, no pressure drop, and T1 equal to T2, and something etc. lah. Tapi bila dekat real life, dia dah jadi light. Kita takkan dapat straight line sebab kita tahu tak ada mechanical device yang 100%. Tak ada yang betul-betul perfect. Takkan dapat straight line macam ni, isotropic process. So kalau sebenarnya compressor pun kita kena kira dia punya isotropic efficiency. From the isotropic efficiency, we know how good the compressor is. So from that, the data of the efficiency, we can find the real state of the state 2. State 2 ni sepatutnya tak dapat straight line macam ni. In real world, kita akan dapat dia sengit. Faham? Okay. So yang ni pun nampak ni ada dia makin menurun pressure dia, line pressure, sebabnya ada pressure drop. So dekat sini pun dia tak cantik dekat saturated. Sepatutnya saturated liquid at state 3, and then in the real life tak ada dah state 3 ni. State 3 is no more. So we have state 4, which is lower pressure, slightly lower pressure than state 2. Dan state 5 pula, dia bukan dah saturated liquid. Dia tiba-tiba ada satu lagi state. Dia dah jadi subcool dekat sini. Okay. Lepas tu dia drop. Okay, dia drop. Pressure 6 ni dia kena tinggi lagi. Sebab dia akan ada drop pressure dekat sini. So to get that state 1, you have to put the state 6 is at higher pressure. Macam itulah. So a little bit of complicated, more complicated than the TS diagram of ideal cycle. This is actual, this is ideal. Okay, awak baca lebih dalam satu-satu. Maybe you want to know more, you can find extra info from this slide, or maybe from the books, or any other legit information source in the internet. Okay, saya cuba ni panjang sangat, nanti awak baca sendiri. Saya akan, kalau ada masalah, so awak tanya saya. So this is our final slide, the last slide of the part 1 of chapter 1. So till now we have known how to define the refrigeration, and we know what is reverse Carnot cycle, what is Carnot cycle, and what is reverse Carnot cycle. We use reverse Carnot cycle for our refrigeration application in our system. And then we know the Carnot cycle is the basic, and they revise the Carnot into the vapor compression cycle. Okay, because the first cycle we learn is about the ideal, yang paling cantik, yang terbaik, but that is ideal, not the actual world. Jadi kita pun masuk belajarlah tadi sikit apa dia actual. Okay, so sekarang ni calculation yang hari ni yang sepatutnya awak belajar adalah example of ideal. So make sure awak cuba buat. Saya dah letak semua pengiraan dalam slide ni, so make sure awak buat, ikut macam mana nak dapatkan jawapan yang saya tunjuk dalam ni. Boleh? So that is all the answers. Make sure you try and get that answers. Kalau lain pun plus minus 0, point something tu tak apa. Jangan plus minus kat depan ni. Jangan yang ni 8, yang ni 2, yang ni 18 ke. Make sure similar to my answers. Kalau lain, okay, tanyalah WhatsApp cepat-cepat. Okay, so I think that's all for today. In our next class, we will okay. Okay, next class saya akan tunjuk macam mana nak kira actual vapor compression if we have the efficiency of compressor. Kita kena consider isentropic efficiency of compressor because we know no compressor and turbine in the world right now is 100%. So mesti ada dia punya loss dalam compressor tu sendiri. So ni cara nak kira